I'm going to talk about ethnic segregation, and what we mean by that is just the unevenness in sorting of pupils into schools according to ethnicity in this case. It's not necessarily, due to unfair policies. It might be, but it's sort of from any mechanism, the unevenness in sorting, basically. Okay. So in the past, when people have measured segregation, they've usually done this using a variety of indexes, and what all of these have in common is that you take your observed data, you apply a formula, and you get a value for the index. So there's been some discussion about what are desirable properties for an index to have, and some debate about what's the best one to use. But really, it has all been this one kind of approach. However, about between 5 and 10 years ago, my colleague Harvey Goldstein, who I should have said this, I should say at the beginning, this work is with Harvey Goldstein and also George Leckie, who's over there. So about between 5 and 10 years ago, Harvey Goldstein and Philip Noden proposed an alternative method whereby instead of just calculating this index, we actually fit a model to the data, and then our measure of segregation is one of the parameter estimates. There is, however, the possibility to kind of link this with the index approach by going on to calculate an index after you've done this. And we just got at the bottom here some examples of indexes that people use. If you've seen any of the previous research, you may be familiar with some of these. Okay, so why would we not just want to use this index approach? Well, there's sort of two groups of reasons for that. We've got problems and we've got limitations. So problems are kind of reasons why we might not get quite the right answer. So the first sort of basic problem, in fact, is that it's not based on the assumption of an underlying process. If we assume that there's an underlying process, that means that each school has a kind of underlying true proportion of ethnic minority pupils, and then the observed values vary randomly around those true underlying values. And so if we have a situation of no segregation, that means that the underlying proportions in each school are the same, but because of the random variability, the observed proportions are different. Now the indexes, because they just measure these observed proportions, will see that unevenness, and they will consider that there is segregation, even in this case when the underlying proportions are all equal. And in fact, the value of the index in that case is going to be a function of the total number in each school and the total proportion in each category. And we're going to come back and talk a bit more about that in a moment. For limitations, there's just a wider range of things that you can do with other approaches you can't do with the index approach. Basically, it's difficult to extend it to look at some more complicated questions. So if we want to look at explanatory variables to try and work out what factors are associated with increased segregation, that's quite difficult with indexes, particularly if we're interested in factors at school or individual level. Also, it's difficult to measure segregation simultaneously at multiple levels. So, of course, we expect that there's unevenness in sorting of pupils into areas, the way that people actually live around the country, and on a smaller scale is uneven. And, of course, that unevenness will contribute probably to the unevenness in school sorting. So what we would ideally like to do is to kind of measure that residential segregation and then get a measure of the school segregation after accounting for that. That's quite difficult to do with indexes. And if we want to look at something like ethnicity, where we would ideally want multiple categories, not just white and non-white, but maybe white, black, Asian, mixed, other, that's difficult with indexes as well. Okay, so what we're proposing, at least what Goldstein and Noden proposed in their 2003 paper, is this modelling approach. So we've got our model here. It's a multi-level model with cohort at the bottom level, school at level 2 and LEA at level 3. And our response is the proportion non-white in each cohort, in each school, in each LEA, modelling that as a binomial. And in this simple model, we're just modelling the probability in this simple way. So we've got an overall, this fixed effect is the overall proportion non-white, kind of in the whole data set. And then we've got a random effect here at the LEA level that allows the LEA proportion to differ from the overall proportion. And then a school level random effect that allows each school proportion to differ from its LEA overall proportion. So these variance parameters here are actually going to become our measures of segregation. This is the variance of the school level random effects. So it's the variance on the Logit scale in the underlying school proportions. And it's kind of a natural measure of segregation, because if you imagine if this has a high value, that means that there's a lot of variation in the school proportions. So some schools have a large proportion of non-white students, other schools have a small proportion of non-white students. That's a lot of unevenness, so a lot of segregation. If we have a small value of this variance, that means that all of the schools have roughly equal underlying proportions. So that means that there's not much segregation. And just a small note, we've got our LEAs as a level in the model here. If we didn't have very many LEAs, we would also have the option to use fixed effects for those, but we wouldn't then get a measure of the LEA segregation. We would, this would still be the school segregation after allowing for the differences in LEAs, but we wouldn't get a measure of those differences. Okay, so how does that actually deal with the problems? Well, this is just a recap of the problems that we talked about before with the index approach. So the model approach, basically, it's allowing for that random variation of the observed values around the underlying values. So it's kind of dealt with that. And we can also get a standard error for our estimates, which allows us to make inferences, which we can't do with the index approach. And with the model approach, our estimate of the segregation is no longer going to be a function of the total number in each school. Now, one reason for that is because we've dealt with this variability of the observed proportions around the underlying proportions. If you imagine if you've got a school which only has 2 pupils, and imagine that the true underlying proportion is 0.5, you can imagine that we get quite considerable variability there, anything between 1 if we've got both pupils are non-white, and 0 if neither pupil is non-white. Whereas if we have a school which has 1,000 pupils and a proportion of 0.5, we'll get much less variability in those proportions. So it's partly because now we're not looking at the random variability around the true values, we're looking at the true values, or at least our estimates of them. That's partly why our segregation is no longer going to depend on the number in each school. But there's also another reason for this. So the index approach, basically, indexes are an attempt to summarize, usually they're based around segregation curves, and they're an attempt to summarize these. So segregation curves kind of underlie the approach that most people take at the moment to measuring segregation. So with segregation curves, what you do is, if you imagine we've just got one area at the moment for simplicity, so you get all your schools in the area, and you order them in the order of their proportion non-white, from the highest proportion non-white to the lowest proportion, and then you plot, going across those schools, you plot the cumulative percentage non-white against the cumulative percentage white. And if what you plot lies on this line, that means you've got no segregation. If it lies on this line, that's complete segregation, and usually, of course, we find something in between. So we've got an imaginary scenario here. First of all, imagine we've got 3 schools in an area, and I'm going to put them on to draw the segregation curve with those. 1, 2, 3. So something to note about this, with segregation curves, the slope of these lines corresponds to the proportion non-white in the school, and the length of the line corresponds to the number of pupils. Okay, so now imagine that we have this hypothetical scenario, and we take this middle school, and we divide this school into 5 schools, but we keep the proportion the same in each. So I've put on here the same segregation curve that we have here for comparison. And if we put the first school on, that's just going to be the same. We didn't do anything with that, so there that goes. The next school has the same proportion as in the original school, just fewer pupils, so it's going to have the same slope but a shorter line. And the same with the next school, and the next school, and the next school. So you can see we're kind of tracing the same segregation curve. And then our final school here is also unchanged. So you can see we've actually ended up with the same segregation curve. So if we use an index approach, which is based around the segregation curve, then we'll end up with the same value of the index for both these situations. What about if we use the modelling approach, and we're going to look at the variance in the proportions of the schools? Well, I've put on the values here of the proportions on the Logit scale. And if we take the variance of those, then that's what we get in this situation. And here are the proportions for our second scenario, and the variance of those is much smaller, and that's because, of course, we have all these very similar proportions in the middle here. So this is actually a difference between our modelling approach as we've implemented it and the index approach. So we regard the thing of interest as being the properties of the distribution of school proportions. So we're interested in, for example, how many schools have the proportion of 0.5, whereas the index approach is interested in how many students are in schools with a proportion of 0.5. So that's the same here, so the index is the same, but the number of schools with proportion of 0.5 is different. I'd like to stress that that's not something that you have to have with the modelling approach. We actually believe this is desirable because segregation is a property of the distribution of school proportions, but it is possible, if you really want to take the other viewpoint, you can use some kind of weighting so that you will actually end up getting the same answer for both of these. Okay, so that's a bit of a digression. With the modelling approach, remember I said with the index approach there were limitations to what you can do. It's quite easy with the modelling approach to extend that. It's a multi-level model, and you can extend it in any of the ways that you can normally extend a multi-level model. So we've got our original model here. We can add in time to allow the segregation at each level to depend on time if we're interested in change in segregation over time. We can add in other explanatory variables to see what's associated with segregation. We can add in more response categories if we want to measure not just white, non-white, but we want to measure white, black, Asian, for example. So we would model that as a multinomial then. I do actually have some slides which go into more detail about these models, but I'm not going to have time to do them now. If anybody's particularly interested, then I can show you those quickly in the discussion if you ask me about those. Okay, so I'm going to show you now an example of some analysis that we've done using this. This is using PLAS data, which I expect you're all familiar with as this is an education session, but basically just to briefly say that it's collected by the UK government, the DCSF, and it's collected for all schools in England. And so we're using data between 2002 and 2008. We want to look at the change in segregation by ethnicity over time. We're using just 3 categories of ethnicity for simplicity, because although in theory you can have as many categories as you want in these models, in practice you can have estimation difficulties if you have too many categories. So we're just going to use 3. And the response is the proportion in each ethnic category in the cohort which enter the school each year. So not the proportion in the whole school, the proportion just in the first year in the school. We're looking at secondary schools in England only. It's basically you start off with the schools which the DCSF uses for league tables, and then out of those we're just looking at the ones which have their minimum intake age at 11. And then after that we drop cohorts which have very few students or which have a big change in proportions, because that's probably due to a mistake in the data if it has a really extreme change in the proportions. Okay, so just some brief summary statistics there. The most important thing about this is that we've got some schools which don't have all of the cohorts. That's not a problem for our model. And we also, however, have some cohorts which are composed entirely of one ethnicity. Again, that's not a problem, but we do have some schools which never have a certain ethnicity, and that probably is more of a problem. I'm going to come back to talk a bit more about that in a moment. Okay. So we've got our model here with the results. So we're just fitting a multinomial model, and we've got timing here, and we're allowing the segregation at each level to depend on the time. We'll come back and look at this in a moment, but I'll show you the graph first of all, because that's a lot easier to understand. So this line here is the black segregation at the LEA level. This is the Asian segregation at the LEA level. This is the Asian segregation at the school level, and this is the black segregation at the school level. So you can see that for both black and Asian students, the segregation from white is greater at the LEA level than at the school level, and that's not surprising really when you consider how different different areas of England are in their ethnic composition. It's kind of not surprising that that's going to be the largest source of unevenness, and that there's going to be less unevenness between schools after you've allowed for that. We can also see that it looks as though perhaps the black segregation is rising slightly at both levels. Perhaps the Asian segregation is falling slightly at both levels. I think probably that's not going to be significant, but we haven't actually tested that yet. So probably it looks like it's staying broadly the same over time, but possibly changing. We are going to test that. And then you can notice that the black segregation is greater than the Asian at the LEA level, but the Asian is greater than the black at the school level, so I guess that's quite interesting as well. If we go back to this table of results, as well as the Asian segregation from white and the black segregation from white, we can get an idea of how the Asian and the black students compare to each other in their sorting. We look at the covariances. So we've got here the covariance between the black intercepts and the Asian intercepts at the LEA level, and that's positive. So that means that LEAs which have more black students also have more Asian students in 2008, 2002. And the same at the school level, we've got a positive covariance here as well. So again, schools which have more black students also have more Asian students. So that's kind of indicating that we've got a pattern that's closer to having white and non-white schools than it is to having white, black and Asian schools. We can also see that we've got a positive covariance between the slopes here, the black and the Asian slopes. So that means that schools which are increasing in their proportion of black students are also increasing in their proportion of Asian students. So it's interesting that that goes together as well. Okay. So that's kind of about it for now, really. We want to do some more work. I mentioned before that there are some schools which never have students in a certain category. And that's a problem because if that's the case, then you'll have a probability of 0, so you'll be taking the log of 0, which is minus infinity, and of course computers, can't cope with minus infinity. And probably this means that we need to fit a mixture model. However, at the moment, there doesn't seem to be any software which will do mixture models for a multinomial response for the number of levels that we want to fit. So it seems that we're probably going to have to be content with this model for now, but be aware of its limitations, and maybe come back to this in a few years when the software will hopefully have caught up. We've just got the reference there to the paper where this was originally proposed.
If I was doing it again, I'd say statistical reflections, because what I'm really going to talk about is where a statistician finds something to do in this field. And I'm talking about what I conceive to be the most elementary problem of assessment. People want to measure abilities of some sort and to do it in an optimal way, and most of them think they know how to do that. Oh, now. Why doesn't that go on to the next one?
Is it down? Is it this one here? Yeah, there. It's little.
You have to keep doing that.
Keep doing that,
Okay.
Presumably you have to press enter on the keyboard.
Well, I'm going to talk about problems which can be conceptualized like this. There is something which I'm going to call loosely ability, which might be primary ability, intelligence, or something of that sort that you want to measure. And I'm going to denote it by Y, and it's going to be in red. In the simplest case, there is some other number, which is a real number that we get from somewhere, which we think might serve as a measure of Y. And the vast part and great part of the educational world proceeds upon assumptions, a very simple and obvious thing, and they arrive at their numbers in various ways. But that's not actually the problem that I want to talk about. I want to talk about this problem, where we're still interested in some particular ability, which is still called Y. Instead of having one measure, we have a whole set of them, which are here denoted by the green X. And they, in some sense, convey the information. People who sat on examining boards of several sorts have been presented with rows of numbers, and the object is to arrive at a classification or a pass or fail thing. Somehow or other, we want to extract the information that's in those X's about the Y. So the question that I'm addressing is the one in capitals at the bottom here, is how should the X's be combined? Now, the world at large thinks they know how to do that. and might not regard it as a sensible statistical problem. And there are some of the most obvious possibilities. You just add them up, which is what people naturally do. If they're a little bit more sophisticated, they will introduce some weights. And any of you sat on examining boards know that examiners have unlimited ingenuity at thinking at different weights which will achieve outcomes which they can see with a gleam in their eye. You might, if n is small, you might just take the largest on the ground. What you're really interested in is the best that a person can do. Now, I say they're all obvious, and at this point you might say, well, what is the problem? Well, the problem is posed if I say, why don't we do something else? Because there are many other functions of those x's which behave broadly in the right sort of way. If the x's were non-negative at ring, why not sum the squares? That will sort of spread the upper range out rather more. Or if you're in the business of finding averages, why not use some other sort of average? What is wrong with the geometric mean? So I give those examples to illustrate that there is a problem, and so we would like to have some guiding principles as to how we might choose suitable functions of x. And I hope that convinces you that there is a problem. Now, I said I was going to explain how a statistician gets into this act, and statisticians start with models particularly. And since the two things that are involved in this problem I call y and x, then we want a probability model which connects the two in some way. And once we've got that, then it's all, at least in principle, straightforward. So I asked the question, are there any plausible models available? And I wouldn't hear unless the answer were yes, and the answer is yes. And, well, there are two in particular that I want to talk about. The first one really goes back to Spearman in 1904, but they didn't know about probability models in those days, and what he wrote down was in fact the mean of this expression. He said, let's suppose every score you get is the sum of two parts, the common part and something else, and he treated those as real numbers, as did people for quite a long time afterwards. But if we were looking at in a modern context, we'd put some distributions on it. We'd make that mu plus lambda I y the mean of a distribution, which for convenience I'm going to take to be normal, and it has some sort of variance. That, as you will recognize, is the linear normal factor model, and in the parlance of that field, y would be called a latent variable because it's a variable, but we can't observe it. So some people call them hidden, but that's really what it comes down to. So that's a very long-standing model, which is a kind of updated version of what Spearman first proposed in 1904. The second one, about which I'm going to say a little bit more in a moment, looks very much like the first one, though as we'll see in a moment it's derived rather differently. It's a probabilistic version of Thompson's bonds model, as I'm going to describe it. But notice that the mean of the distribution depends on a parameter involving I, and the variance depends on another parameter involving I, so there's a superficial similarity there. I should say that these distributions are, of course, conditional distributions. I'm talking about the distribution of x conditional on y in both cases. I should have made that explicit in the notation, but I haven't done so. That last little bit is to make a link with the next slide, because I want to say a little bit about Thompson's bonds model. And it's basically this. He proposed this in about 1914, I think, for reasons which I'll explain in a moment, and not simply to provide an alternative tool for measurement. He supposed in the brain there were things called bonds, and he was quite honest, he didn't know what a bond was. It might be a neuron or a neural network or some assemblage of brain matter which comes into play when a person sits down and tries to do an item. The word bond he got from somebody else, I've forgotten who just at the moment, but he took it over and used in much the same sense. We suppose that when a person sits down and attempts any kind of item of this kind, a certain proportion of their bonds are called into play. So Pi is a parameter characterizing the item, and it's something like the difficulty. If P is big, It means it needs a lot of bonds to do this job, and if it's small, it doesn't need so very many. Each bond contributes something to the total score, and I call it here an amount EJ. So an actual test score is conceived of in this model as being the sum of a lot of increments derived from the activity of different bits of the brain. The last bit he didn't have, but I put in to make it a probability model, and nothing in that last line is very critical. I'm assuming that EJ is normal, they're independent, they have a mean, mu, and a standard deviation sigma, and it doesn't really matter if they vary from bond to bond, but I keep them that way to make things as simple as possible. So that essentially is the model which Thomson proposed as an alternative to Spearman's, and it's largely been forgotten, and I've been part of an enterprise to resurrect it. But those two models are almost indistinguishable statistically. At least they're indistinguishable as far as their correlation structure goes, and it's correlation structure that people deal with in this thing. Spearman knew, and it's easy to show, that the correlation matrix, the row, would have this rather neat structure, product of two of the lambdas. Whereas Thompson showed that in his model, it had exactly the same form, but the two parameters were the square roots of these proportions. They're necessarily positive quantities. Actually, Thomson never really proved that. He did it by sampling experiments to begin with. He tossed about 6 dice, when adding the total gives you something that's roughly normal. That gave him one random variable, then he added another bit. And he says that he carried dice about in his waistcoat pocket. And when he had a few moments to spare, he'd get his slipper out or something and toss these things. And there are early papers, and there's one in the Proceedings of the Royal Society, in which he does this, and he shows that if you did this, you get a matrix with basically the same correlation structure. Later on, he produced a kind of mathematical argument for that result, but it isn't a complete argument. What he did was work out what was the most likely disposition of bonds, and then show that if that was the true, that would be the correlation. It is in fact true regardless. He was in fact replacing random variables by their expectations. And Mackintosh in his book, I think it's called IQ and Intelligence, reproduces that argument without apparently realizing that it is not. But it is true, and one can show by proper probability arguments that this was actually why Thomson produced his model in the first place, or at least why he tried to sell it. He said, here's everyone going around thinking that Spearman has cracked the problem of ability. There is a basic underlying ability. What he really wanted to show was that there was another model which gave something which was statistically indistinguishable from it. And that's something which we're all familiar with, and something that you need to know, that because a probability model fits, it doesn't necessarily describe what's going on. There are other similarities which I won't go on to. Now this is the, if you have limited attention span, this is the moment to pay attention, because this is the real nub of the thing. My original question was, how do you combine those x's to tell you about y? And the answer is contained in the first bullet point. Being statisticians, we regard the x's as random variables and the y also, because they're things that the fact that we can only observe one and not the other doesn't really make any difference to their status. And the model was defined in terms of the conditional distributions of the x's given the y. What we're really interested in is going the other way about and finding out something of y given the x's. So what we want is the distribution of y conditional on all that we've observed. This will encapsulate all the information the data has to tell us about this unknown thing. Now, that might be a very unpleasant expression, but in a great variety of cases it turns out to be very simple. And certainly it's simple in the two examples I mentioned, but not limited to them by any means. It turns out that this posterior distribution depends on the x's through a single function of the x's. So that's telling you there is one unique way in which you can summarize that data which will tell you all there is to know about the x's, assuming you've got the model right, of course. Everything here is conditional. So what are they? Well, this is what they are. They're both linear functions. And there are a very large class of problems where the answer to the question that I posed is that it is a linear function. So all those people who've been forming weighted averages and just adding things up have been doing the right thing all along without really knowing it. There are unknown parameters, of course, which would have to be estimated. And I'm not saying that either of these things estimates or predicts anything. What I'm saying is that any predictor would have to depend on the x's only through those things. And you might need to fit models to find out what to scale them by or do other things. Now, the Thompson one I think is particularly interesting because it doesn't involve any parameters. It says that if that model is a fair description of what is actually going on in the brain, then really all you need to do is just add up the x's. And anything you do with it subsequently will depend on that. That, I think, is actually a rather fundamental and important thing which needs repeating very often. Now, I come back to this again in a moment, but supposing that model doesn't fit, it took a long time to persuade Spearman that was the case because he collected large amounts of data and all his matrices did satisfy that, and he wrote a book really adjusting, applying his thing. But eventually it became clear that it didn't always fit. Now both of these models provide a very natural way of extending things. If there isn't one, why there might be more than one. In the Spearman case you can just add extra terms onto the mean of y in the obvious way. And it turns out you can do very nearly the same in Thompson's model. I'm not going to explain or justify what is written in that last line. All I want to draw attention to is the fact that the form of the distribution will be pretty much the same. You have to introduce the p's, remember, probabilities of selecting bonds. You have 2 goes at this now. You do it the first time and you do it the second time. The first time maybe focusing on, say, the arithmetical properties of the item, the next time on visual or spatial things. That's an important question which I'm not going into. And there will have to be other parameters in there to describe what's going on. I'm coming back to that in a moment because that's the important thing. But there's a paper by 3 authors, Ian Deary, his professor of psychology here, and Martin Lawrence also in the university. We've done quite a number of things on this, and but what I've been describing is particularly in this paper in Psychological Review earlier this year, New Lease of Life, Thompson's Bonds model. It would be a very interesting study in the history of ideas to work out why Spearman won the day, as it were. Partly, I think, because his model could be generalised to quite other fields in a way that Thompson's couldn't. But the history of all this is extremely interesting, but I posed at the beginning the question as what is a statistician's business in there? And you may be dissatisfied with the answer, because the answer which I've given is it says, roughly speaking, you ought to take weighted averages of x's. And you can imagine a lot of customers saying, thank you very much, you've just been gilding the lily, we've been doing this for years, and it's nice to know that you approve of it, but it doesn't actually change anything. I want to suggest 4 reasons why approaching the problem in this way is important. 2 of them are standard traditional ones. This is the last thing. One would to say, well, now you've got a good reason for believing in this model. Or to put it more charitably, you can say, well, if you compare the sort of look at it intuitively, if you think you ought to add up numbers, you are really behaving as if this were true. That's one kind of argument which is commonly used. Another one is commonly used, once you've got a model, you can compute standard errors, goodness of fit tests, and all sorts of other things. And that is true, but of course it's conditional on the model. Everything statisticians do is conditional on the model, and that's something I think of a disadvantage. But there are 2 other reasons which I think in this case carry more weight. One of them is that it makes it much easier to see how to generalize this thing, and that's why I don't know how to go back, but the one before this, I indicated how one could introduce new variables, because in effect, in posing those models, we really pose families, or at least it's not very difficult to establish them, extend them to a family, of which we take in particular things. So if things don't work, you have a way to go. The final and fourth reason, I think, is that it provides pointers for empirical research. In this paper, we've got quite a long section on does the biology of the brain favour one or other of these models? Thompson said, and this is years and years ago, biology really has to decide. But it's not simply that, because it has all kinds of implications. Now, in my innocence, I thought that after all these years we knew a lot about the brain. It turns out we don't actually know a great deal about the brain, though we know a lot more than we did. The only thing that seems very clear is that neither of these models can be a very accurate description of what is actually going on. There's a lot of knowledge which shows that what goes on in the brain is extremely complicated. But the arguments still seem fairly evenly balanced. There are things in people studying the brain which suggest discrete elements which are involved in mental operations such as answering these things. And there are others which have to do with various sorts of matter in the brain which seem to be continuously varying subjects, which would favour Spearman's idea that ability does vary in a continuous fashion. In fact, I don't think the difference is that important, because if there are bonds, whatever a bond may be, it's likely there are very large numbers of them, maybe millions or billions or even trillions, because the brain is an extremely complicated thing. It doesn't seem to matter very much whether this thing that you all have varies along a continuum, or whether it's the sum of a very, very large number of very small things. Cyril Burt actually had a rather neat way of summarising. He says you can talk about a bushel of wheat as a bushel of weight or a sack of grains. And whether you're talking about in the grain level or in the sack level, it doesn't actually make any very much difference. But I think there's clearly a lot to go. We think, when I say we, I mean the authors of this paper, think there's a lot more mileage in using Thompson's model than in using Spearman's in fitting data of this side, and that's what we're currently engaged on, but I'm stopping.
Yeah, this research, governing by numbers, is a study of quality assurance in England and Scotland, funded by the Economic and Social Research Council, but it's part of a wider study of quality assurance in Northern Europe, entitled Fabricating Quality in European Education, which is funded by the European Science Foundation. Well, that's the credits done. Global pressures mean that quality assurance is a pressure on all education systems. But in this particular presentation, I'm going to focus on England, where performance management has taken its most extreme form. All right. So the story I'm going to tell you today is starting off with the role of numbers in governing education in England, and I'm going to tell you how over the past decade governments have developed a touching faith in data and numbers. There's been a massive growth in the production of data about pupils and schools, and in the process this has provided wonderful opportunities for private enterprise to make a profit out of it, but also created some problems as well. Although this particular research project has not specifically looked at the effects on pupils, teachers and schools, there is a considerable body of other research that looks at the unforeseen consequences of all of this. And finally, I get to the data dream. And here is the fantasy about perfect data. And I must confess that as an educational researcher, I've spent most of my working life trying to get better data on pupils and schools in order to do research. Well, in this case, I'm going to tell you a story about a system where people in power have had this vision of wonderful data and what it can do. They've had the power to make it implemented. But as I tell you the story, you'll wonder whether it's perhaps a cautionary tale for people like me who should not dream about better data. So, the role of numbers in governing education, and it's perhaps illustrated by this statement from a recent government policy document, which was in support of the white paper, Building a 21st Century School System. And they say, our data are used to monitor and drive up performance, increasing accountability at school, local and national levels, and providing a basis for our partners to make informed decisions. So you see, data has this magic power to drive up performance. Well, how does it drive up performance? How can you take the promises made by an education minister in Parliament to drive up standards by X% and actually make it happen in schools? Well, the answer seems to be in this day and age that all partners in the education system should value the data and internalise the targets and work towards them. And that data, this pure data that is completely objective and clean, can also be used to provide evidence so that you can know where to focus on, you know what works and what doesn't work, and so on. So that's the role of numbers. But let me remind you about the structures of the accountability system in England, which are being developed since the 1980s. And very much over this time, there's been this mushrooming of the use of data in order to force change in school education. Until the 1980s, perhaps the governance of education could be characterised as trusting the professionals, but increasingly trust has been replaced by performance management, quality assurance, derived from business practice. So now we have national curriculum, national testing to set national standards. And I should say that England has got the most onerous system of national testing, with standard assessment tests, the SATs, given at the end of year 2, year 6, year 9, followed up by national examinations in year 11. And the publication of school-level data in a form that can be used to create the crude league tables, both of the SATs data and of the examination data. And then parental choice, encouraging parental choice of schools that's informed by the league tables, so that every stakeholder in the system realises that the only thing that matters about a school is their average levels of attainment. And parents are under tremendous pressure to choose the right school for their children based on average performance. Then again, it's all backed up by the inspection by Ofsted, and I'm going to say a bit more about this in a minute. But don't forget also the use of data, targets for school improvement, and appraisal of teachers' performance. So, going on to my second part of my structure, the production of data by schools, the production and analysis. And as I said, since the 1980s, there's been this massive increase in the collection of quantitative data about pupils and schools, steered by the inspection processes, with a very high-profile naming and shaming of schools that were deemed to be underperforming. In a way, data were being used as a weapon to beat schools into submission so that they would do as they were required. But since 2004, we've had a system of intelligent accountability. And now the underlying principle for intelligent accountability is that schools should be learning organisations capable of rigorous self-evaluation and planning for improvement on the basis of evidence. But what that actually means is that schools must constantly produce and analyse data by self-evaluation. Self-evaluation is the key, but schools are now producing the data, analysing it, setting targets for the pupils, for the teachers, for learning targets, and so on. And this process is inspected using short notice inspections. Now, in the past, before 2004, schools had several weeks' notice if they were going to be inspected. And they could spend those weeks in very, very stressful production of data and information so that they could give a good performance to the inspection team. But now, there's just a few days' notice, so they have to be on top of the data all of the time. They have to be constantly doing their self-evaluation in the required way so that when the inspection happens, they've got it all there at hand. So we've got this tremendous production of data in schools, the analysis, a sophisticated analysis going on as well. But the data is then flowing into government agencies. Pupil-level data on characteristics, attendance, behaviour, but specifically attainment is the key one. And the system being used to for this data to flow across the system is RSS Online, which was created by Ofsted and DCFS together. And this system is constantly live, constantly requesting updates and new information, so that and the speed with which the data move and the technical capacity means that data analysts are preoccupied with constantly updating it. One of our informants described it as being like a coal mine, whereas instead in the past you were shoveling coal into a trolley. You're now shoveling data into an online system. And at the end of the line, this goes into the National Pupil Database, and I'm really grateful that Becky's mentioned this already. The National Pupil Database has data on all the pupils in state-funded schools and is constantly being updated. When a senior official was interviewed about this, they described it as the bridge from which they steer the system. And they described it in these words, that we corral all of this data and information, and we can glance across all the local authorities, and you can look at all the key performance areas, and that's actually across social care areas as well as education. So at that level, we're doing quite active performance management of the system, and that's a really powerful tool. And so this is the system whereby the promises made by the minister can be effective in terms of benchmarks, targets, and so on, and the process of change and the process of evidence of achievement can be monitored. The National Pupil Database. And I'll come back to it again in a minute, but just to say that in the process of all this data production, it's really is big business. It's created tremendous opportunities for multi-level companies, for all sorts of non-governmental organisations, charitable trusts and so on, are now involved in the data production business, testing database systems, statistical packages and so on. Very, very sophisticated tools that are being provided for school managements so that they can be constantly analysing their data and be on top of what's going on. And of course the computer technology is increasingly an important part of the flow of data. There is, again, a touching confidence amongst government that private enterprise can provide sophisticated systems efficiently, transparently, and cutting costs. However, our interviews with some informants in the local authorities and elsewhere in government suggested that actually there were some problems along the way. One of which was the most high-profile problem of the standard assessment tests last year. And this was very much in the news because a multinational company was given, successfully tendered to administer the standard assessment test to 11 and 14-year-olds. The contract was 156 million for this work over 5 years. But there were problems with the administration, and very, very quickly into the news came reports that head teachers in schools bitterly complaining that their tests were not being marked, that the results were not being back to the children, and so on. And the whole system ground to a halt. So when the QCA went in to sort out the process, it found 10,000 unanswered emails from desperate teachers and markers, and eventually the company was sacked. That was a high-profile one, but there were other suggestions by our informants that there were problems of lack of continuity between suppliers, which led to inconsistency and unwillingness to take responsibility for any problems. So other unforeseen effects identified by other research are particularly, there's a strong body of evidence that the high-stakes use of quantitative data, especially the publication of school league tables and the public naming and shaming of schools, has detrimental effects on school education, and particularly the polarization of school intakes, increased problems for schools at the bottom end of the league tables. But also other effects within the school in terms of practices that are taking place. And because of the focus on high-stakes testing. There was a report by the House of Commons Select Committee which took a lot of evidence on the effects of high-stakes national testing in schools. And this is part of their report. They found that national test results, using national test results for the purposes of school accountability, resulted in some schools emphasising the maximisation of test results at the expense of a more rounded education. They looked at a variety of classroom practices which distorted the education of children and so on. They went on to say that we find that teaching to the test and narrowing the taught curriculum are widespread phenomenon in schools, and that the focus on improving test results could compromise teachers' creativity and children's access to a balanced curriculum. So it was a pretty damning report on the unforeseen effects of national test results and the use of these test data as measures of school performance for accountability. Quite a damning indictment of the effects that it had in distorting education. So I'd like to go back to my data dream. As I said before, I know quite a lot of people like me, thanks, have this dream that, well, if we could just improve the quality of data, look how much more we could do in terms of educational research. But my data dream is nothing like the ambition of the vision that is held by those in England who have been devising this system and thinking about what they could do with better data. And again, this was an interview with an analyst at DCSF who spoke about, we've got all this key stage data and it's longitudinal, and we're probably the leading administration in the world as far as value-added measures and schooling are concerned. And when I think about the quality of the data, the amount of data, the abundance, I'm just about drooling at the thought that one could have all this wonderful resource for educational research. Certainly, it's not something that we have in Scotland to work upon. But just the story that I've told you about this, all the work that goes into creating these data. And there's ongoing problems with national tests in terms of just ongoing disputes about the marking and so on. Certainly there are upward trends in attainment. I mean, it's succeeded in driving up levels of attainment as measured by these measures. But then there always seems to be countered by claims, particularly in the gutter press, that actually the exam, it's just that the exams are getting easier. But then there was a report just a few days ago about GCSE, the examination that, depending on whether you included coursework in the examination, it seems that girls get better results if there's coursework because they like to work hard all through the year, whereas boys do better if there's less coursework in the exams because they like a quick, risky test at the end. But what does that mean? What are the implications of that for the data that we're using to analyse the system? If the data measures can be skewed so quickly by whether or not you have coursework or not. But then, as I've mentioned already, the high-stakes nature of a lot of this data has led, it seems, to manipulation of test results in order to improve performance, such as teaching to the test and so on. And finally, what does it say about, I'm so sorry about my cough. What does it say about comparing school performance? I mean, over time, there's been a tremendous amount of very justified criticism of crude league tables. And so the reaction has been, well, let's get better measures. Let's have value-added tables. Let's have contextual value-added tables to take account of deprivation and so on. But at the end of the day, how valid are these measures? They're still questionable. And so, finally, I can't really come to any conclusions, but just some final remarks that we've argued that data have become central to education policy and that government places a great deal of trust in numbers. But data have their limits and they don't by themselves offer solutions to policy problems. They've got to be interpreted. And the effort to collect more and better data places considerable pressure on the education system, and it is extremely costly. So I wonder, is it time to put data back in its proper place? And of course, its proper place is giving me good data for educational research and not to steer the system. So on that, I'll stop and just say that there's quite a bit more information on our website.